Okay, so let's get started. A little bit disclaimer first. I know the abstract said Node and Postgres. The technique that I'm going to be talking about is generally applicable to any RDBMS, and there's only a few points that are actually Node specific here. So with that out of the way, the situation that we developed this technique in is that we're a small business-to-business enterprise web accessibility shop. So we do a lot of testing and remediation for clients who are much, much larger than we are. So in order to sort of keep up with the needs of our clients, we want to try to minimize our infrastructure and streamline our processes as much as possible. To do, for example, a multi-tenant trial server that we can later break people out of and move them to full instances, possibly do some analytics to see how people are actually using our applications. But our problem is that since our tenants are so much bigger than we are and have their own needs and their own wishes for actually managing the pace of upgrades, we can't do true software as a service. So that is out because one tenant may want to work with an older version for as long as they want to, and we're just trying to keep up and release new stuff. So the problem for us is sort of how do we have our cake and eat it too with regard to having a multi-tenant capable setup that we can later pull data sets out of. So fundamentally, our problem is we've got too many databases floating around out there. At one database per tenant, we have dozens of clients, dozens of databases. It's a lot to manage. And so any way that we can reduce this and bring these together and consolidate them as much as possible, that's just less to have floating around. It's less to deal with. For us, this matters because of time, money, and effort. We are a pretty small company, especially relative to our clients. So the less time we spend juggling databases, configuring things, re-indexing, doing maintenance, the more time we have to actually develop software. Money, I'm perfectly happy to spin up an M4 large and just leave it out there for a couple of months, but other people seem to object to it. So if we can just pull these together, have fewer databases, we have less maintenance costs, less server costs, and it's a lot to deal with to just juggle all these, remember where everybody is, and be able to pull stuff in and out of their databases and manage separate versions. So we can have a multi-tenant application with one of three possible database architectures. We can do separate databases, one per tenant, which from a data perspective, this is not an improvement, it's the status quo. We want to be able to do better than that, if at all possible. It's sort of our last resort. Next option, with a little bit less overhead, is to have a single database with separate schemas per tenant. This is better for us because we have fewer things floating around, but another thing is that it does allow version independence. We can have one schema at version 1.1, one schema at version 1.2, and so on and so forth. But it's got still a lot of application security overhead. You have to have different users and manage access privileges to the different schemas, just like you would have for the databases. You have to juggle connection pools, which is a bit of a pain. And analytics are still pretty difficult if we want to do those, because you have to stitch together result sets of the separate queries for separate schemas. The third option is partition tables, which is it's actually pretty great. It's got the lowest server overhead. Security and access becomes strictly an application concern. There's only a single connection. Analytics, everything's just right there. So if at all possible, we want to do this. So if we get started designing a schema for partition table structure, this is sort of a reduced version of one of our accessibility testing products. So we have a tenants table where we have a single row per tenant that we're looking at. Each tenant has users and tests, which are related by a junction table. Users have devices which they use to perform the tests and raise issues. So the problem for us with this schema is that how do we work at the level of individual tenant data sets, so the tenant row and their related rows in these other tables. So if we have tenants in a shared database, if one of them buys a standalone license, like we had an insurance industry client move to a standalone server recently, so we need to be able to pull their data out and just give it to them in a tidy little package without everybody else's stuff coming along for the ride because they probably don't want anybody else to see just what sort of shape their sites are in. So most of you probably know SQL Server. This is a Postgres dump script. This is a fairly standard way to throw data around. Postgres has pgdump. MySQL has MySQL dump. SQL Server, you got to go through a couple of context menus and wizards, and there's a generate scripts option. Oracle is the exception here. It's got a binary dump format. But what it's doing here is it's saying to copy into this table these rows, which are tab separated, and it goes field by field. So if we have something like this for our entire database, can we generate that? Something that only has the data for the tenant that we're interested in. So the ways to do this, the first thing we can do is just attack it with a blend instrument and just go for a brute force, just pull our data out as we can. So to do that, given the schema, we just take it from the top. We go to the tenants table because that's going to be our entry point. We pull out the row that we're interested in, and we just pop it out into our output. Moving on from there, we go to the users table, pull out the users related to that tenant, dump them out to the output. From there, devices, and you start to see a pattern here where the further you get from the entry point, the more complex your queries are. So your exporter complexity is going to be essentially tracking schema complexity. The more complex your schema, the more complex your exporter. This becomes also especially problematic if you have something very complex where you have converging schemas. For instance, if devices can be accessed through another table, say tests, you have to get not just all devices which are linked to tests, but all devices which are owned by users. And you have to do a lot of thinking to figure out, okay, how do I get all the devices for this tenant through any or all paths that we could have them? You can also track intermediary IDs and use in lists to pull out these data, but it's not really much better. Another major problem is that it's very fragile. If you make any major changes to your schema, you have to come back in here and do some maintenance and update your exporter. You can ameliorate this to some extent by automating the columns part of it, by pulling out those from the result data set. But if you add a table, drop a table, rename something, juggle relationships a bit, you're going to be back in here doing work, and it's thankless and crappy. Fortunately, we can approach this a little bit better, in a better way, if we go back a little bit and have a sort of a discrete math refresher. So a graph is fundamentally a set of vertices connected by edges. The definition of a vertex or an edge is abstract to a greater or lesser degree, but it should be consistent in that you should be talking about the same sort of thing when you talk about a vertex or an edge. There's lots of things that are represented as graphs in the wild. Everything from hiking trails could be a graph where the path is an edge and stations along it are vertices. Network topology diagrams are graphs pretty much straight up where your hardware, your routers, switches, workstations, those are vertices. Communications going back and forth between them are edges. Also, if you shop on Amazon or Zappos, you can frequently see sort of people who purchased this product also bought this, that, the other. Behind the scenes, that's a graph. Products are vertices, and the act of purchasing or having multiple purchases in somebody's account is an edge. There's a specific sort of graph that we're interested in, though, which is a digraph or a directed graph. The only difference here is that edges have a directionality. So for here, there's an edge going from A to B. There is no corresponding edge going from B to A in the other direction. So some examples here would be stuff like social media follows. If you follow somebody on Twitter, they don't necessarily follow you back. So that constitutes a directed graph between you and that other user. Package dependencies are represented as digraphs in everything from NPM to Maven, NuGet, and stuff like RPM or the Arch repository. Those generally come in as trees, which is sort of a special case of a digraph where you don't have convergence. So B to D and C to D, if you pull those out, you have a tree with the root A. Oops, that's a button. But crucially for us, another example of a digraph in the wild is foreign keys. A database's relationships make up a directed graph. So if we can somehow represent our schema as a digraph, we can start to manipulate it and do things with it to start pulling out related data. So if we have to first define what our vertices and what our edges are going to be. Our vertices is pretty obvious. It's a table, or more specifically, a set of data within a table, or set of rows. So for us, we're just going to say that every table has to have a primary key constraint so that we can query it consistently. This includes junction tables, which are going to be vertices in their own right. Even though in ERDs they're frequently elided, you just have one edge going between the two tables that are related by the many-to-many relationship. So our vertex is going to be a table name and a collection of primary key values. Our edges are going to be the relationship. You might note that this is actually a little bit backwards. The source is the referenced column in the relationship, and the target is the referencing one. You have to think about it in terms of dependency rather than who owns which columns. We also have to store the actual columns that make up the key. For example, if it's possible to have multiple relationships between the same tables, if our tests can have a user who created the test and a user who's currently assigned to it, we have to track both of those relationships in order to guarantee that we have an entire picture of the data set. So this is a representation of our schema as a digraph. So if we can start traversing these relationships and just bounce around between them and just cover the entire graph, this is not going to be any kind of fancy pathfinding thing. It's just, let's visit everywhere and pull up everything that we possibly can. If we can get a connected subgraph, so some rows from this table, some rows from this table, some rows from that table, all related, that gives us a single tenant's entire data set in isolation that we can work with. To actually get this, we need to start querying the metadata of our database. The ANSI standard defines an information schema, which allows you to query your structure and your metadata just as you query your other tables and your actual tables and views. Everybody implements it to varying degrees of conformance. These are often views on implementation-specific tables. Postgres has the PG catalog. SQL Server has the system catalog where you got the sys.tables or whatever. But for us, there's 3 specific items we're interested in. Table constraints gives us all the primary keys in the entire database. Referential constraints do the same for foreign keys. And finally, key column usage tells us for a certain key which columns actually make it up in a given table. So the next step for us is going to be actually building our subgraph, which you're going to have to do through a fairly involved recursive process. So we start, obviously, at the entry point. Just as a side note here, we could start anywhere. We just need a table name and a primary key value, and we can pull out any data that's somehow, somewhere related to that row in the table. But it's easiest because we know the tenants. That's going to be sort of our obvious entry point. Just go with a tenant ID. And our process is going to be, we add first the primary key information to the vertex. Then we start scanning for foreign keys that involve that vertex. For us, there's 2 of them. There's users and tests both have a tenant ID. The order in which we take these is completely arbitrary. It's easiest for us to go just alphabetical by source for consistency's sake. So we start creating an edge, but we don't know what the primary key values are on the other side of it. So we have to actually recurse along the edge as we're building it to get the vertex information for the other side and complete the edge. So we do that. We go to tests, add the test primary key information to that vertex. We finish the edge, and we just do the same thing all over again and scan for foreign keys involving tests. The first one for us is going to be issues with our scheme. So we do the same thing. We start building the edge. We recurse. we finish the edge by adding the primary keys to the issues vertex, and then there's only the foreign key backup to tests. And this is the first time that we hit our recursive base case, which is we're not adding any new information at all, because the edge direction guarantees that any issues are going to belong to tests that we already covered. So instead of recursing, we roll back up to tests, and then the next foreign key is actually going to be device ID from tests. So this is the first edge that we traverse from the target, but it works exactly the same for us. We process the vertex the same way. The only real difference is that because tests has device ID in it, we already know the primary keys, but it's really easiest just to treat it exactly the same way. So after devices, we recurse to users. And same deal, we add the vertex, add the primary keys, but scanning the primary keys does reveal that we could have incomplete information. Because we came to devices from tests, there could be devices that users have that they haven't started testing with at this point. So we don't necessarily have all the devices for that tenant, even though we have all of them for that tenant's tests. So we actually wind up recursing back to devices, which brings us to another sort of edge case here, pun not intended, where you can have multiple vertices existing for the same table. If we go back to devices, because we're going to have devices that overlap, users have them some in tests, some not in tests. So we'll just consolidate those in order to make sure that we don't have the same row in devices appearing multiple times in the directed graph or in multiple vertices, which would then cause them to appear multiple times in our output. Because if we do that, we try to insert the same thing multiple times, crashes and burns, and it's useless to us. So in complex schemas, however, you could have rows that you get to from multiple paths that do not overlap. And in that case, you can have multiple vertices. Looks a little bit weird if you have the same block of inserts or copy statements for the same table multiple times, but it's harmless because the same data does not appear in both. So all users' devices does overlap, so we merge the new entries into the existing vertex, and then we hit the base case again, which is that there aren't going to be any new tests because the only new devices that we've added aren't being used in tests. So we roll back up to users, and then just like with devices where we initially only got those that are being used in tests, since we're only looking at the current vertex and its neighbors, the entry point is really just another table. So we could theoretically have another tenant connected to some of the users that we just picked up. We shouldn't. It would be really, really terrible if we did, because that would mean we have some sort of pollution going between individual tenants' data, so it's connected. We don't want that. But we have to just go back up and check. But also, we could have users that don't have devices. So we need to go back, double back up here, and pull out all the users related to that tenant, and just make sure that we visited every row in that vertex. So we do that, and the last table that we haven't visited is the junction table. So we go in there, even though there's a compound key, it's the same deal for us. We're already just building the edge, getting the full primary key of the junction table out, adding that to the vertex. The many-to-many relationship does imply that it's possible to have a test that is not related to a tenant, so we have to go back there just to make sure. And at that point, we mapped out the entire connected subgraph. We have all the rows present for that tenant in our vertices. So you might note that we haven't base cased all the way back up to tenants and recursed to users. There's no need for that because we've actually already visited users from tenants, so we have all the data that we need. There is one caveat here. These will mess you up. If you have, for instance, a JIRA-style scheme where impact can be, trivial, moderate, minor, serious, critical, blocker. You have a lookup table is a common pattern for approaching this, where you have just a table with keys mapped to the values for the impacts, or any other situation where you have sort of an enumeration. If you do that, you can start coming in from one tenant, recurse into the issue impacts table, And then you start looking for any issues that have impacts with those primary keys, and suddenly you've got your entire data set out there, and you don't want that. In Postgres, we sort of sidestep the question entirely. We use enumeration types, which are a custom type that you can create that converts a string visible value into a number in the backend, so it's more efficient for indexing. But for other DBMSs that don't offer that functionality, you would have to look at defining some sort of stop table to say, if you reach this table, don't recurse from it, just assume you've hit the base case and pull back out. So at this point, we have the data set. How do we actually convert that into a script that has the single tenant data that we can pull out into somebody else's database? So toposort is sort of a graph theory function where you order vertices by dependency. This is how package managers decide what order to install things in, for example. The way it works is that you start by looking at the vertices which are not targeted by any edges. So we're going to start with tenants. We're going to query the full rows from tenants. We're going to script those out to our output, which for us is going to be standard out. If you use Visual Studio, the console, because from a command line application, what we can do is we can take standard out, pipe it out into a file, or put it directly into the input of another command. So pull tenants out, we remove the vertices and edges that we just looked at, and then we just repeat that same process until we have nothing left in the graph at all. There's one possible snag we could hit, which is that if you have a cycle anywhere in your graph, you're basically screwed. The good news is you have to really, really try to get this. Specifically, you have to at some point stop enforcing your foreign key constraints. Because the only way to insert, or the only way to generate a cycle is to insert data before data it depends on. So you can insert one row here and another row and then turn on foreign key constraints, and suddenly you have a referential integrity problem because you have a cycle going between the two and you don't know which is the source and which is the target. So to get started with the toposort, we take our tenants, we just generate that copy statement and push it to our output. That frees up users, which we treat the same way. Pull it out, pipe it into the output. Devices works pretty similarly. And that frees up for us the tests, which you might notice that this is not a JavaScript date, it's a Postgres date. As we're pulling this information out, the driver that we're using, and this is the one specific thing for Node, the PG driver includes column type information. So we can use that to pass our results out to a formatter and pipe them through there on the way to the output. If you don't have the type metadata in your results, you can use the Information Schema columns tabular view. And that includes type information that you can just correlate with your output and make sure that you have your results coming out in the format that your import will expect. So the last two tables for us with all our edges and other vertices gone are issues and user tests. The ordering doesn't matter here since they're at the same level, so we just pipe those out in whichever order. So, great talking about it, but how about you actually try it out? I've created the example schema that I've been using. I have a data set generated for that, so we can actually pull that out. It's kind of weird typing on that screen. So all the databases that we have, Arachne is the name of the application. It's after it's after the Greek weaver in mythology who had the bad idea to challenge Athena to a contest and got turned into a spider for her troubles. And PSQL is the command line client for Postgres that'll let us actually query the data and look at what we actually have in there. So here's all the tables probably look familiar. I've got the same set. I've got data for 3 tenants in there. So Acme, Cespetas, place to place. And they've all got users. We've got users for every single one. Actually came out in more or less the same order. There's a bit of a mix-up there, which is good. So we exit out of there. Actually run Arachne, and it tells us how to use it. We pass in connection options. We give it the name of an entry point table and a primary key value. Like so. Turns for a little bit and then generates all of our copy statements in the order we expect. So it starts with tenants, it moves on to users and devices, pulls everything out in the dependency order that we were looking at with toposort. So if we pass it a different primary key, we get another tenant's data, we get Cespetas here. So let me make sure I dropped that first. Okay. So now, given this output, if I create a new database and apply the schema, because this is a data-only export, I have the schema generation statements already in a file that I can just run against this database, and it'll create the setup that we're looking at. And then I can run Arachne again, and because it's outputting to standard out, I can use a pipe to just hook the output of Arachne into the input of PSQL, and it will run those statements in the PTP database. And you can see they're just copied. I'm standing in the way. It copied everything out that we're looking for. And if we go back into PSQL, into the new database, we can see we only have the single tenant now, and the single tenant's users should show up. So there we have that. And where's the mouse? Come back here. So yeah, this is on GitHub. I'll get to that in a little bit. But for us, what this has allowed us to do is to treat a such and such data set as a logical unit that we can work with, so we can back up individual tenants. And this is the thing that's made it possible for us to run with the partition table setup as opposed to a multiple schema setup, which makes things it makes my life a lot easier, which I'm always in favor of. So we could have a situation where we have all 3 tenants in a single database and turn it into that. Just pull out, extract a single data set, put it anywhere we want. We can restore them. We can back them up on independent schedules. We can keep independent backups. So this has ramifications for removing tenants, for data retention policies. We're really just scratching the surface of what we can do with this so far. Other big selling point here, conforming to constraints is a big deal. ptdump orders by dependency by default. MySQL dump doesn't. If you have a MySQL dump script, it will actually turn off your foreign key constraints, run all the inserts, and turn the constraints back on. This is actually kind of dangerous, because if something goes wrong, then you're left in an inconsistent state with your foreign key constraints off. But ordering by dependency lets us take this scenario that we had just from pulling PTP out, and we can throw everybody else into that database without downtime. This is honestly more of a cool hypothetical than something we've actually had to do yet, but being able to apply the output of Arachne into another live database means we can offer things like tier downgrades for shared servers. There is another sort of bonus usage, which is as a schema validator. If you dump out your database and restore a single tenant and you have data missing, then you know your foreign key constraints are not complete, and you know more or less where to look. It's where you don't see any data. So being able to handle arbitrary schemas saves us from having to do exporter maintenance. We can take any data set from anywhere. We could use alternate entry points. If for whatever reason we wanted to start with a specific user and just pull out their entire data set, we would wind up with exactly the same output in the same order, because we would visit the graph, go back all the way up to tenants, and then that would be the first one that gets topo sorted out. So something else this let us do is another developer and I at DQ have been working on a fairly major change recently. It's been, I want to say, probably a couple months, actually. We got rid of our users table. Everything about users is now supplied by Keycloak, a single sign-on provider. So this has been an absolutely huge code change for the application. So we've been tearing stuff out, revising tests, revising the entire infrastructure to handle users coming from somewhere else. But this didn't have to change at all. It worked exactly the same way. We had to do no maintenance at all. So it's been just great, because I would probably have forgotten about this until the last minute, and it would have been horrible. So one of the cool things about working at DQ is they let us get away with open sourcing our tooling. So I put this up on GitHub as sort of a reference implementation for the technique. I want to say this is sort of a final note. This doesn't make the partition table strategy the automatic solution. You could have requirements for medical or financial records where you are required by law to segregate your tenant data. Or if you have architectures where tenants need to be able to interact with each other, then you're kind of stuck. This is not going to help you with those. But for what we do, where we have tenants that are completely apart and just living in the same space without interacting or sharing any data, means we can ignore the major pain points of the partition table strategy almost entirely. So it's made that a lot easier for us, and well, that's it.